Everyone. It's great to be here. For me, it's actually really close by, and that's really nice. E-ink started in the Cambridge area, I think 25 years ago. I was not at E-ink at that time, but moved to the Billerica area like about 10 years ago. So it's all close by, half an hour drive. Let me see. So today I will go through the background of electrophoretic displays, and then also bring it to where is the state of the art now and where are things going? How do you make products with electrophoretic displays, etc. I heard this is a scientific conference, so I had to put a few formulas on a slide. These are the only formulas you will see. And I keep it really simple. So what is actually electrophoretics if you talk about displays? Electrophoretics is a broad field, but if I talk about displays, it is charged pigment particles and charged inverse micelles that are put into a non-polar oil-like solvent. And then you bias two electrodes so that the pigments start moving. And if they are moving towards the viewer, you start to see them. Now, those pigments can be any color, and the oil can have a color or be colorless. And we will see a number of examples later in the slides of how such a system can work. Important is that those pigments are typically modified. There's a lot of organic synthesis going on, polymer synthesis around those pigments to create shells. And those shells create a zeta potential. That's proportional to the surface charge, the Debye length, and then divided by the dielectric constant. So that is all put into the panel between two transparent electrodes. And then the dielectric or the electrophoretic velocity is again proportional to this zeta potential and inversely proportional to the viscosity of your medium. And of course, it goes linearly with electric field. So that's the basic principle of how such a display works. That looks really simple, but it has been a really hard thing to make it to work in practical applications. That's also where I want to start a little bit, very quickly go through the history. 1973, this was one of the early display technologies with a high potential. LCD was researched at the time as well. And NEC was one of the pioneering Japanese companies who has been working really hard on this. And the promise, of course, was it is Lambertian in reflectance. So the particles reflect at all angles. So your viewing angle is really good. It doesn't need a polarizer. And we will see later, if I compare it to LCD, OLED, other technologies, that they all use polarizers. Polarizers have one big disadvantage. They filter out at least half of the light. So when you don't need a polarizer, you typically get much higher reflectance in your panel. And it is a simple stack. So from a cost perspective, this could be an interesting proposition. Now, the issues were NEC could not get it to work at the time. There was roll-style instability. This has to do with the fact that particles really move in this system. With LCD, you just have rotation of molecules. Here, particles really move. And you get roll cells that are typically having dimensions proportional to the cell gap. And you see an example of that on the right-hand side, that black and white photograph showing the roll cell. Gravitational settling. If you put it vertically for a weekend and you come back, you see that the particles have moved down. No permanent image stability was achieved, which is difficult because that means you need to reset the panel every time you switch it. And there was migration to the electrode edge. So if you have pixel electrodes, there are gaps between those electrodes. Typically, the particles would move to the gaps and not be mobile anymore. So NEC gave up on this. And then if you jump forward, 1990s, LCDs came. Electrophoretics was still in a research stage, but actually a bit given up on. And at that time, LCD could not replace paper. Paper has a high contrast, high reflectivity, wide viewing angle. It is flexible. Large areas, of course, possible, lowest cost for one book, and you don't need a battery for paper. While LCD had updatable information, wide access to content, you could play video on it even, and if you have a lot of books on it, it could be an economical option. but it's not paper-like. The reading experience is not great. And every day you need to charge it a few times even if you read a lot. So fast forward again to 1997 when e-ink started as a spin-out from the MIT Media Lab. And there were a few big breakthroughs, actually two real big breakthroughs, and that was encapsulation was proposed to solve this roll cell instability and the gravitational issues. So you encapsulate the pigments into small capsules, like 20 to 40 micron big. And then that prevents this roll cell, but also the gravitational settling. Permanent image stability was achieved. This has to do with kind of a gel-like behavior that you get when the pigments don't move. And this has to do with specific additives that were added to this internal phase, this ink. And it is a roll-to-roll production process. It is still being done. We have a factory about 1.5 hours drive from here in South Hadley, Massachusetts, where we use an old Kodak coder to make large amounts of this film for display applications. So with that, we now have paper-like viewing, wide viewing angle. It's easy on the eyes. The power consumption is really low, and I will come back to that later. You only need to drive the panel when you want to change the content. So when you don't want to change the content, the image is still there, but you can power it down. Always on and sunlight readable. It's lightweight because we are actually coating it on plastic. Plastic substrates, typically 4 mil, 2 mil, that is 100 micron, 50 micron PET with ITO on it. And shatterproof, of course. So one quick slide to introduce e-ink, and then I will go into more the technical side of things, what platforms we have. So e-ink spun out in 1997, was acquired by a Taiwanese company called PVI, specialty LCD company, in 2009, and PVI renamed itself to e-ink Holdings. E-ink acquired Cypix on the West Coast in 2013, and I will come back to that later. And it's now since 2004 on the stock exchange in Taiwan. Large patent portfolio, about $1 billion in revenue last year, and e-ink is growing pretty fast. It has doubled its revenue over the past 3 years. So although it's already a 25 years old company, especially over the last 3-4 years, the growth has been really fast. And about 3,000 employees. So what is typically the expertise that e-ink has in-house? It's quite a wide range, actually. If I start on the left, we do a lot of chemical engineering, chemical synthesis, capsule manufacturing, all chemical work in order to functionalize pigments, to add specific additives that are also synthesized in-house, to get the right charges into the system and get the right mobility of particles in the system. And also a lot of analytical technology that we need to use to characterize everything that has been made. So a big analytical department as well. Then we do thin film manufacturing. So in the middle photo, you see a big piece of film that was coated in our South Hadley plant. And we really measure our coating campaigns that we do on a day in kilometers. And that then goes on a roll towards our customers. So a lot of material science, device physics, thin film manufacturing, but also adhesives. Adhesives are an integral part of our film. And we need special adhesives that have a certain amount of conductivity. And then the last piece on the right, and that's mainly done in our Taiwan facilities. It's how do you, after that, make a panel with it? This is done with TFTs, TFT design, manufacturing. We source our TFTs from different companies, the well-known brands, and then they are assembled in our assembly line. So that's all the expertise we have in the company. Now, quickly, I mentioned that we acquired Cypix on the West Coast. It's now an integral part of e-ink. This was 2012. And now we have two platforms. So I did already mention on the left our microcapsule platform, where we have 2 or more different particle types in a clear non-polar fluid. And the layer thickness typically 10 to 40 micron. And it's really easy to coat for large areas because it's kind of an ink that you can put on a coater and then coat on PET ITO. On the right is the microcup platform, where the end result is actually very similar, but the way to make it is quite different. And I will come back to that in the next slide. This is a system where we emboss a layer first, and that embossing actually creates the containers again to put your ink in. And this gives very tight layer control. And that also is the reason why, and I will talk about color in a few slides, but why color first started in a microcup platform. Because tight layer control means you can switch them in a very accurate way. And when you want to do color, that's what you need. So how do we make these? Again, on the left, microcapsules, on the right, microcups. And this is very high level, but you can see it's very different actually. When we start with the microcapsules, we start with all the ingredients that go into the microcapsules. So that is the non-polar fluid, the particles, the micelles. That is then emulsified in water. And we have special materials that then create a shell around those emulsified droplets. And that is what we call the microcapsules. Of course, you have all kinds of different sizes at that point. So you need to purify and classify, as we call it, so that you have the right cut of the size distribution. And after that, you add a binder. And that actually is kind of what we call a slurry, an ink, that you can then slot die coat on a PET ITO film. On the right-hand side, the microcup flow, where we actually start by putting a layer of organic material, a resist, on the PET ITO, and you emboss that. The embossing creates containers, typically hexagonal container shapes of a certain height. That can be all from 30 to 10 micron in height, depending on the product we want to make. And after that, it's actually a relatively simple coating. You fill it with your internal phase. And then kind of a difficult step is you add a liquid sealant on top of it that doesn't mix. And you solidify that by UV. And that actually creates your film. So the end result is quite similar, again, in terms of thickness, in terms of what is switching. But the way to get there is quite different. And the one on the left, the microcapsules, is really good for making large amounts of wide area sheets, while the one on the right, because you do embossing, has certain size limitations, but gives you very tight layer height control. So once you have this, how do you make a display out of it? It's actually pretty straightforward because our film ends with an adhesive and a release liner. So you can take any backplane, it can be a segmented backplane, it can be a PCB, and you then take a piece of our front plane laminate that's typically cut to size from a roll, remove the release liner, and at a certain elevated temperature, you laminate it on the backplane. Then you need a second step, where you laminate what we call a protective sheet on top. And this is for UV protection, moisture blocking, not moisture blocking like you see in OLEDs, where you need a very tight oxygen and vapor control. But in our case, it's more food packaging. You need to keep it in a certain humidity range. Otherwise, it doesn't switch well anymore. So you laminate that on top, and then you have an electrophoretic display. And in the cross section, you see an active matrix electrophoretic display and all the layers we have there, where we also include driver ICs, the FPC, and they have a system board. There's also an edge sealing around that is typically just an acrylic that is printed around the edge to block the moisture there as well. So pretty straightforward process, and that's also one of the strengths. We can enable customers pretty easily with making panels with all kinds of backplanes. So E-Ink enabled what we call the revolution in e-reader. And this happened already in 2004, starting with Sony, and then it really took off when Amazon launched the Kindle. So still, e-ink is the medium of choice for e-readers around the world. We have a lot of different customers, and is one of our major revenue drivers still. Although e-book and e-reader and e-note, note-taking devices are starting to blend at this moment. So we see more and more e-readers that can also be used for note-taking. Lately, they expanded also into color. E-ink was black and white for a long time. But over the past 5 years, we start to see color, and I will get back to how we do that in the coming slides as well. And there's a second really big revenue driver at this moment, and that is electronic shelf labels. Also started black and white, and now using this cup system that I described before, we are starting to add, besides black and white, we start to add a red pigment or a yellow pigment. And in the end, we had black, white, red, and yellow pigments. So this continues to become more complex and more colorful. And more big players in the supermarkets and retailers are starting to adopt this, because the value proposition is really good for them. They don't need to change paper labels anymore. They can just press the button and update their prices. This market alone is now for e-ink measured in square kilometers of material per year. So it's a pretty big market as well, and growing quite fast. So how do we make color? The first thing was a very straightforward thing that actually most display technologies do, and that is if you have something in black and white, you can add a color filter to it on top. We call this area color. So if you want to make red, 1/3 of your area is red. If you want to make green and blue, same, 1/3 of the area you're using. And I mention that specifically because lately we actually moved to a different system where we don't have that constraint anymore. And I will show that in the next slide. So the nice thing is customers can easily upgrade because their whole system will stay the same. They still drive a black and white ink, and now they get color. And that is also the majority of what you saw in the e-readers that were going to color. The majority of them are at this moment using a color filter technology. But we have gone further over the past years. And this is really one of the big focus areas in the company. And that is we are introducing colored pigments now. So the trick here is that if you have more than 2 pigments, you have a positive and negative one. And then the question is, how do you actually sort those? Because you don't have a 3rd or a 4th type of charge. The way we do it is you can charge particles with different zeta potentials. You can have very negative, a little bit negative, very positive, etc. Particles can have different sizes, and there can be all kinds of specific interactions between particles. And by engineering this well, you can find ways to always sort them out and create the right colors. Doing this either in a way that creates very bright colors or in a way that is very fast is kind of what we are playing with for different markets. So on the left-hand side is what we call Spectra 3100. This is used in price tags. And this is showing what I mentioned in the previous slide, where we have now price tags that can do 4 different colors. Also some mixed colors. By mixing the red and the yellow together, we get an orange color, for instance. And on the right-hand side, what we call gallery, but also prism. This is using white as the reflector, like paper, and then CMY subtractive color. This means that depending on what kind of color particles are above the white, you create a certain color by filtering out a certain part of the spectrum. So the nice thing with both platforms, all pixels can show all the colors. So we are not having area color anymore like with a color filter. And that increases the brightness by about a factor of 3. Then we have a number of applications for the gallery and the prism. One is e-readers, e-notes. But the other, and I will show that in a slide that is coming after this, we can also cover big surfaces with this film to make color changing objects. And we did some pretty cool stuff actually with BMW on this that I will show later. So to finalize a little bit the slides on what are we doing in color, what are the pros and cons, I do want to give one little bit of a busy slide showing what actually the promise of electrophoretic now is. If you can do all colors in one pixel with our CMY wide system. For that, I'm making a comparison between OLED, the LCD that is backlit, an LCD that's reflective, and then on the right-hand side, an electrophoretic system. And it also goes back to the very first slide where NEC started to work on it and what they thought was the promise. And now you can also see that that is really becoming reality here. So starting with OLED, it's an emissive technology. It is typically between glass or plastic substrates. It needs a polarizer, otherwise you look into a mirror. And a polarizer gives you about a loss of 50% of the light. Then you use a color filter there. So only 1/3, and actually a little bit less of that is giving you the right color. So there's quite a bit of losses in there. And it needs to be on to show the image. As soon as you power it down, image is gone. So high power, but also high speed, can be above 100 Hertz. LCD, it is kind of similar in that it is emissive, but also very different in the stack. And those are also the advantages of OLED, of course. OLED is thinner because it doesn't need a backlight. It only needs one polarizer. So an LCD starts with a backlight, then an entry polarizer, where you lose, of course, 50% of your light. Then, depending on how you switch your LC, the polarization state is changed or not. And that causes actually the light to either go through or be blocked at the second polarizer. Pretty straightforward. And then a color filter in between again to create color. Same thing, again, more than 50% loss because you have two polarizers here. 2/3 light loss because you use a color filter. Again, on to show an image, high power, and more than 100 Hertz speed, so it's pretty fast. LCD reflective, very similar, but now the backlight is actually moved to the top and becomes a front light. And you only need one polarizer because at the back you have a reflector. But the principles stay the same. You still have a reflective polarizer and a reflector. The polarizer is used twice now, incoming and outgoing. And in that sense, the same as the OLED and the LCD backlit. LCD reflective has been tried quite a bit over the years, but given the large amount of light loss, typically reflectivity is not high enough for real commercial applications. So we have not seen reflective LCDs becoming mainstream. You saw them in the low-end watches a little bit in the early days, with a front light as well. Then go to electrophoretic. The nice thing there is that you don't need a polarizer because the particles just reflect the light and give you everything you need without a polarizer. You can make all colors per pixel. So I showed here in all the examples, red and green coming out of those color filter panels. In an electrophoretic panel, you can just make 3 times yellow, while the red and the green would combine to yellow as well. So you have 3 times the intensity, we could say. You could also make 3 different colors with those 3 pixels. So you also have 3 times the resolution, you could say. It's only on to update the image. Extremely low power, and I will come back to that in the final slides. But it's a little bit slower, up to 15 Hertz, and I will show that in a few videos. Because you have different product lines with different speeds for different applications. So those are the principal differences, and that is also why E-ink is doing quite well at this moment. It is high brightness and low power consumption, and especially the low power consumption is becoming more and more important in the world. So a few videos showing what the performance is so that you get a sense of how those panels are working. This is a large tiled advertisement display, so 9 pretty big displays tiled together, using that color filter technology with black and white below it. You can see it switching a bit and then quickly settle to final state. And of course, after it is at its final state, it's powered down. So it's not consuming any power anymore. Purely reflective, there's no front light on this panel or on these panels. The next one, This is gallery, so this is the subtractive wide CMY, very high resolution because you can make color in every pixel. And you can see switching a little bit slower, but it has an extremely high reflectivity and a high resolution in color. So this is used now, for instance, this is a pocketbook prototype. They've announced that they're going to launch this year with this technology. And this is now being designed in with a number of customers. And then the last one, this is Spectra 6. So I talked about the ESL, where we go for really bright colors. This is a platform where we can do full color with reflective particles, extremely bright. We didn't optimize for speed. So this is more where a customer wants to put their billboards in a certain state at the start of the day in a store and then keep it there. Because you can see switching actually is quite a thing. It takes about 12 seconds. But the important thing is that after that, you get an extremely bright image that looks like a real paper poster. So if you are having a store and you want to update it, let's say once or twice a day, you can use this in order to replace your paper in your stores and create very bright poster-like signage. So from that, I would like to cover a couple of application areas that you can find electrophoretic displays in at this moment, and go a little bit into why people are actually adopting electrophoretics there instead of other technologies. So here you see an overview. I will go over that quickly. You have education on the left, smart office below that. Those are more CE application, consumer electronics for note-taking, etc. Reading. Mobile, wearable, also such an application. And then below that, smart hospital. Really interesting because in hospitals, one of the things that people want is displays that are not emissive in rooms, because that is seen as a problem for patients, but also a very simple way to convert hospital rooms, because you don't want to close them off for a day, but want to go quickly in, update it, and go out again. And the panels that we provide are reflective, but also battery powered. So you don't need to pull wires, etc. You can just put them on the wall, and they have Wi-Fi enabled communication with the central systems in hospitals. So this is gaining traction quite a bit. Smart transportation, solar powered signs. You see them in Boston also quite a bit using electrophoretic material. The nice thing is, again, is you can just put them down somewhere. You don't need to pull wires because they're completely powered by a solar panel on top of the pole. License plates, a little bit of an odd thing. You see them now in California quite a bit, a number of other states as well. The dealers really like it to put some other messages on it while they are selling the cars, but it's also convenient because your renewal of any of the license plate stickers can be done remotely, automatically. Smart retail already discussed, retail signage also discussed, industrial tags. In industrial, we also have quite a bit of volumes. Flexible displays, logistics. We also have a tag now with Alaskan Airlines for luggage, and foldable devices. So in the next slides, I will go over a number of the specific applications. I mentioned already that e-ink is now being tried more and more as color changing surfaces as well. This is a bit of an extreme example, the BMW, a concept car that was made for the CES this year. Last year we had it in black and white, this year in color. This will, of course, not be something that you will really see in mass production on the roads, but it is something that kind of inspires the people at BMW, at e-ink, to think about what can we do in the future. So I have a nice movie here with a little bit of sound to keep you awake. has 240 color panels. So it's not really a wrap in that sense, but it's a number of panels with a wrap over it. And also some black and white segmented parts, but mostly color parts. Completely synchronized updating of the color, and really used for BMW to create quite a big splash on the CES. It was, I think, the keynote there. From this, there are also a whole range of practical applications that people are now looking for in not only automotive, but also in other segments where you want to have color changing services. One that's a little bit different, but also automotive, is AGC has integrated our black and white film into a panel. And as you can see here, they have dichroic glass, and then they switch our material behind that, and that gives some sort of a waving color experience that they are promoting now for use in automotive interiors. Also being announced at the CES last year was Lenovo on laptops. So if you want to have like kind of dual use, you can have an OLED panel as your main panel, and on the back you can have a low power electrophoretic panel. And if you just want to do note taking or want to read for a while, you can twist the whole screen and make actually the electrophoretic panel your main panel, and start note taking or start reading. And this is, I think, on the market right now as the latest model. This is a really interesting application. Very simple, just a black and white, simple screen that can show whatever someone is saying. And the application is actually that you put it around your neck, you start talking, and the person who you talk to can see what you are saying. So if you're deaf, or if you don't understand the language, you get real-time translation. Or if people cannot hear, they can see what you're saying. It's now being rolled out. It's a startup. And this could be a really good application for electrophoretic technology, because it doesn't consume any power and it doesn't update it. Fossil is already on the market with a combination of a traditional watch with electronic features. And this is the latest that they're showing. So a traditional watch where they have like features of heart rate, steps that you take, and it's all shown on the watch. One last thing as an application I want to show is e-ink is now also going into different areas. And one area that is really interesting is everything around switchable glass. Initial application more for automotive, sunroofs that need to switch. But of course, if you think further down the road, this could be very interesting for buildings as well. And people always associate it also with heat management in buildings. And there is definitely an angle there as well, if you engineer the films well, that you can use this for heat management. This is still in development. It's bistable. So again, you can put it in any switching state and it will stay there. And one of the other things that is really a good selling point here is that the black that an electrophoretic panel has is a real neutral black, while most other competitors are either doing kind of bluish or another color instead of black. So last piece is more on sustainability, becoming more and more important actually in our company, but also in society in general. We are a member of the UNGC, and there are a number of aspects where the electrophoretic technology in general is a really strong position for, let's say, the low power and easy on the eyes, etc. Aspects that you need for future displays. Typically, if you look at our panels, for instance, an e-reader, you charge it once a week, once in 2 weeks, depending on how much you read. While tablets typically need to be charged every day. And this is really because of the consumption of the panel itself that is extremely low. So a few examples. Here's the e-reader, where we compare an e-paper e-reader using electrophoretics with an LCD tablet and with a real paper book. And then have a user scenario where you read 10 books a year, 300 pages in a book, and roughly 1/3, you can make about 10 books out of it. So if you do that with an e-reader, you have 540 tons of CO2 equivalent. Then if you do the same amount of reading on an LCD, your footprint is about 50 times higher. But if you do that just with paper books and use those books only once, it is much, much higher. This is, of course, not the complete life cycle, because there's also something like waste at the end and recycling. But it shows during usage what the advantage is. Second one, the ESL, electronic shelf labels, even more extreme. And the reason is that the shelf labels are only switched about 4 times a day. That's the scenario we have here. So that means that while an LCD is on for the whole day, an electrophoretic panel is only switched 4 times a day. So the energy advantage is way bigger. And you can see that here, where now the LCD tag used as a retail label is 12,000 times less energy efficient than an e-paper tag. While paper tags are even worse. This is also one of the reasons why retailers are switching. On top of that, there's a lot of labor involved if you have paper tags. And the last one, and this is a bit of a simple one actually, it's when you do transportation, like in bus stops or train stations, and you do e-ink signs there that are powered by a solar panel. Of course, you don't consume any power from the grid. While LCDs cannot easily be powered with solar panels, it just consumes too much. So they always need to have a connection to the grid. And with that, they consume much more power. Of course, this also requires complete life cycle analysis, but this is purely for the usage scenario. So that brings me to my last slide. The electrophoretics have already started like, how many years now ago? 50, I think it's now, 1973. With NEC looking at it, a lot of promise. And now finally, we see it as one of the display technologies growing and growing. We now have typically OLED, LCD, and e-paper, still as the smallest, but it has its niche and it's growing. And it took quite a while. Display technologies in general are taking typically about 25, 30 years to come to maturity. We've seen it at OLED as well. And e-ink is still growing. We now see it in more and more applications. And in this slide, you can see a number of the application areas where you can now find electrophoretic displays. And especially when you go into stores, the US a little bit less, I think, but in Europe, in Asia, and now also starting in the US, you will see that in stores, price tags are actually mostly using electrophoretic panels. So with that, I would like to thank you for your attention.